Today we're going to talk about geometric sequences. Previously we talked about the arithmetic sequence, where consecutive terms have a common difference, where we are adding the same number from term to term to term. Remember, when we were subtracting, we actually added the negative. So in a geometric sequence, there is a common ratio between consecutive terms. Each term is found by multiplying the common ratio to the previous term. So as you can see in the example, we are multiplying by 5 each time. So the first term is a 1, times 5 is a 5, times 5 is a 25, times 5 is a 125, etc., etc. So when you look at this sequence here, we have the first term is a 1, second term, each of those in line is called a term, and then the value of the term is the 1, the 5, the 25, and the 125. The common ratio is down here. You see the same thing happening over and over and over through multiplication. So next we want to talk about how we continue and extend a geometric sequence. Well, when you look at the next 3 terms, what we first have to notice is how are they going up. Well, if I look at 1 to 3, I could look at plus 2, but then when I move on to the 3, it would be a 5, so it's definitely not a common difference. But I look at the plus, the common ratio, and I'm looking at taking the second number, 3, dividing it by 1, and I get a 3. So I would basically be saying times 3. I go to the next number, 9 divided by 3, and I see also times 3, and then 27 divided by 9 is times 3. That's the easiest way to kind of figure out the common ratio. Obviously, sometimes you can look at it and say, oh, 1 times 3 is 3. The best way to figure it out is think of the second term divided by the first term to help figure out what is the multiplication part. So to extend this, I would then just say times 3 more times basically. And my next term in the sequence would be 27 times 3, which is 81. 81 times 3 is 243, and 243 times 3 is 729. So that would be the next 3 terms in that sequence. Looking at the next one, again, if I look at these and I start trying to figure out what is actually happening, notice here our number is getting smaller. So we start thinking division, but we are still always thinking in common ratios as times a number. So we're going to be multiplying by a negative 1/2. Notice how the sign is going to change every other time. Times a negative 1/2 again, and times a negative 1/2 one more time. Okay, so then my next 3 terms, negative 10 times negative 1/2 is a 5, and then the next term is going to be negative 5 over 2. You don't need to make it 2.5, and then my next one is back to a positive 5/4. So you just got to keep noticing how the sign was changing back and forth. So now we want to look at how to graph one of these. So when I'm graphing a geometric sequence, there's a couple of things that I want to keep in mind. So when I'm looking at the geometric sequence, unlike when we graphed our linear equations, a geometric sequence has a discrete domain. Remember when we talked about our domains for being discrete or continuous, the discrete meant that it only could be specific numbers, and the continuous meant that it could be all of the numbers that go in throughout that. It's a continuous domain. When I think about my x and y table here, when I graph these, the position, or n, is actually my domain. Well, I can't have a number in a sequence that is the 1.5 position. It's either the first position, or the second position, or the third position, or the fourth, etc. It can't be part of a position. So because of that, it's a discrete domain. So that's one thing we've got to keep in mind. So we also are not going to have any negatives when we start looking at our x and y's. I shouldn't say that. We could actually have negatives for the y's. In this table, we don't. Our positions, though, would always have to be positives. So we're going to end up with first quadrant really only. So what I'm going to do is I'm going to just kind of graph the table real quickly, and then you can come back and check, see if your graph looks just like this. So here I put in some scale. I put in the scales of 4s on my y-axis, and I put in just regular 1s on my x-axis. And then if I just kind of start going and putting in the different points, I've got 132 up top. I've got 216 at the second position. 3, 8 is my next position. I have 4, 4. And then I have 5, 2. Now what you're going to notice here is I'm not going to connect the dots. Okay, so we do not connect. And again, that's because we're talking about a discrete domain. But there is something that I want you to notice here, is that what do you notice about these points? Well, hopefully you're seeing that, but they appear to curve. Remember when we did the arithmetic sequences, we saw things that were linear, and basically because the common difference was basically giving us a slope, adding the same number, either positive or negative, over and over and over again. Now we are seeing things that are more exponential because we are multiplying by a common ratio or common number over and over again. So we're going to kind of build this table and just kind of talk about this. So because consecutive terms of a geometric sequence change by equal factors, the points of any given sequence with a positive common ratio rely on that curve we just showed you. You can use the first term and the common ratio to write the exponential function that's going to help describe the geometric sequence. So here's how we're going to do this. So here in this table we have the positions we just talked about. Position 1 would be the first one in the sequence, followed by the second, followed by the third, followed by the fourth, and etc. to the nth position. So what position we see. Then secondly, we want to talk about the term. So the term we're going to refer to as the a sub 1. When using a sub 1 and r, okay, when we think about it in the first position, really all we are going to do is say it is just a 1. The very first term in position, the common ratio is not really involved, it's just the first term. When I move on to the second term in our sequence, that was when I would take the first term and multiply it by the common ratio, so it's a sub 1r. When I move on to the third term, again, I would take the first term and multiply it by r to get the second term, but then I'm going to multiply it by r again, so really I'm multiplying it by r squared. When I get to the fourth term, again, the first term times r, which is r squared, times one more r is now r cubed. And what we want to notice here is what is happening between the number with the sub number, our term number, as well as the next one in the sequence with the position. So when I get to the a to the nth, what I want to think about here is, well, we just said it was the first term times the common ratio, and notice when I look at my table, I end up with r to the 1 less than the a. So what I mean by that is if I look at the second one, the second term, a sub 2, is to the r first power. a3 is to the r to the second power, or r squared. a4 is to the 3. So what that is basically telling me, the pattern is the n, which is the position, minus 1. And then you'll notice down here, this is the formula that we're dealing with. A to the sub 1 times r to the n minus 1. So here would be like an example. So let's say we have the number 1 to start our sequence. We have a common ratio of a 5. So my next number would be 1 times 5 is 5. The next number would be 1 times 5 squared is now 25. The next number is 1 times 5 cubed, which is now 125. Okay, that was the sequence we saw in the front. So the sequence was actually 1, 5, 25, 125. Now what that looks like as far as our equation to the nth term is 1 times n5 to the n minus 1. And then this is the formula that we just were referring to right here. So when I'm trying to write the equation for a geometric sequence, the an is the nth term. So if somebody said, I want to know the 7th term, that's going to be in that spot. The r is the common ratio. How are we multiplying from term to term to term? A1 is the first term. So in the example to the far right there, I started with the number 1. That's the first term. And then n is your position. In the sequence. Alright, so let's just see how this works. Okay, so here's a real-life application. We're talking about clicking the zoom out button on a mapping website doubles, kind of important there, doubles the side length of a square map. Square is kind of important there too. We're given a little bit of a table there that gives us this information. They didn't really even have to give us this, except we kind of needed to know where to start. But we know doubles means times 2, which is what they are kind of telling us. And then in the table we kind of get that also. So times 2. So remember, this is my common ratio. Okay, so that is my R value. When I look over at the other side of my table, we can see that the different clicks, the first click, second click, third click, that's basically going to help us figure out the position in the sequence. This number 5 here is basically going to be our first term. Okay, so that is the first term. Okay, so we want to write the equation for the nth term. So we could certainly just keep saying times 2, times 2, times 2, but we want to know, well, we just need the equation, because what if somebody says, I want to know the 100th term? I'm not going to go times 2 100 times. So what we want to do is use the formula we just looked at. We know that the common ratio is my R, and the A1 is my initial first term. Well, 5 is my first term. The common ratio is 2. And n minus 1 just stays as n minus 1. So how I'm going to figure this and use this is like this next example. Find and interpret A8. That is basically saying the 8th term. Okay, so here's how the formula goes in. So instead of writing an, I'm going to write a8. So I'm basically kind of like our function notation showing that this is the 8th term I'm looking for. And then I plug in 5, common ratio of 2. Now I plug in 8 for the n. So a8 equals 5. Don't make this times right away. Remember PEMDAS. We've got to do the exponent first. And so when I look at that next number, I would then next do a to the a8 is 5 times 128. Remember PEMDAS would say do the exponent next. And then so that would mean that the 8th term is going to be 640. So about how many clicks is, on the zoom button, is the side length of a map that is this many miles. Okay, well, that basically is saying we want to know what is that. So instead of me having the term, we're trying to figure out what is the term. We are now looking at the value of that term. Okay, so what I'm going to have to plug in is this 2560 on the left hand side. We still have the n minus 1. And this time we're now solving for the n, the number of clicks. This is the number we're looking for. So my first move here is to actually divide by 5. You know, that 2 is still attached to the exponent. So my first move is to divide by 5. When I divide by 5, I get 512, 2 to the n minus 1. Now, there's a couple different ways we can now solve this. We can start looking at how to get to this answer. What we do want to think about is, can I write 512 as a base 2? On the right-hand side, we have 2 to the n minus 1. So if I can write 512 as a base 2, that would be ideal. I actually can write it as a base 2, and it is 2 to the 9th. And because I can do that, remember when we said we had the same bases, we could take the exponential expressions and make them equal to each other. And then I would just add 1 to both sides to get the n by itself, to get n equals 10. So to solve this, 10 clicks to get 2560 miles.